Off Cape Vogel, near Boga Boga in Papua New Guinea, roughly 150 to 165 feet below the surface, rests the Boeing B-17F Flying Fortress known as Blackjack. The aircraft, serial number 41-24521, sits largely upright on a sandy seabed just off the fringing reef. It represents a strict constraint boundary for aviation archaeologists and underwater heritage managers. Under Papua New Guinea cultural property protections and modern archaeological best practice, the wreck is treated as a site to be documented with minimal disturbance. Investigators face a rigid mandate. They must positively identify a heavy bomber and document its condition without treating the wreck as a recoverable pile of parts. The physical footprint of the site is massive. The aircraft measures 75 feet from nose to tail and spans 105 feet across its main wing. At a depth of 164 feet, the bomber rests just beyond the reach of continuous surface wave action. This specific depth provides a dual reality for any survey operation. The water column above shields the wreckage from the worst kinetic energy of surface storms, thereby preserving the aluminum structure. However, that same depth imposes severe physiological limits on investigation teams. Bottom time is heavily restricted. Divers cannot linger to slowly excavate or shift debris. Every minute spent on the sand requires strict gas management and limits the amount of operational data that can be gathered on a single dive. The heritage boundary therefore closes the normal forensic recovery path. Cranes, lift bags, structural removals, and laboratory teardown cannot be treated as responsible survey options. The survey must therefore rely on visual and optical methods, accepting that much of the internal evidence will remain behind an aluminum shell that should not be opened by tools. Despite these operational restrictions, the initial visual assessment of the site yields a critical piece of structural data. The bomber is not a scattered debris field. The fuselage, wings, and tail section remain largely joined as a continuous unit, even though the airframe shows visible damage from the ditching and decades underwater. The aircraft appears to have entered the deeper water as a mostly complete machine rather than as a cloud of separated fragments. This continuous geometry confirms that the aircraft did not experience the kind of catastrophic breakup often seen in high-energy water impacts. A bomber of this size and weight hitting the ocean surface at the wrong angle could shatter under massive hydrodynamic deceleration forces. The fact that this specific aircraft retained so much structural continuity indicates a controlled and survivable water landing. That condition changes the investigative problem. A typical water impact would scatter engines, wing roots, and fuselage sections across the seabed. Blackjack instead presents a largely continuous hull, forcing investigators to concentrate on what the intact structure conceals. Any close inspection must therefore be planned around the openings and surfaces already available. The team must establish a baseline condition of the aluminum skin, engine cowlings, and control surfaces while avoiding accidental contact with the wreck. The primary objective of the modern survey is to establish a permanent, verifiable record of the aircraft. To achieve this, researchers must overcome the visual distortion of the water column and the inherent risks of deep water operations. The restriction against physical sampling means that visual data is the only acceptable proof. Every measurement and every structural assessment relies entirely on the line of sight. The untouched state of the wreckage provides an unparalleled historical baseline, but it severely limits forensic extraction. The aircraft must speak entirely through its external geometry. If the bomber survived the initial impact completely intact, investigators must now determine what operational failure forced a perfectly good airframe into the deep water drop-off. The geometry of the flight path on the night of July 10th into July 11, 1943, forced a critical operational trade-off. Returning from a night bombing run, the 10 crew members faced severe weather and serious trouble with the 2 engines on the right wing. The loss of reliable thrust on one side of the aircraft created an immediate aerodynamic drag penalty. The flight crew could no longer maintain the safe return profile they needed through the storm. Fuel exhaustion moved from a distant concern to an urgent operational threat. The heavy bomber could no longer be counted on to reach its intended airfield. The operational objective shifted instantly from completing the return flight to executing a survivable descent over a dark ocean near the Papua New Guinea coast. Operating under these severe flight constraints, the pilot in command handed the aircraft over to co-pilot Joseph Moore. Moore possessed previous water landing experience, a critical asset for the impending ditching sequence. He had to manage a damaged, asymmetric aircraft while descending in poor visibility. With both right-wing engines giving serious trouble, the aircraft naturally wanted to yaw and roll toward the weaker side. Attempting a blind water landing across the swell under those control limits could have driven a wingtip or the nose into a wave face, flipping or tearing the airframe apart. To reduce that risk, Moore appears to have prioritized a controlled ditching path near the reef, using the sea state and shoreline as the only available reference points in the darkness. This parallel approach required the heavy bomber to skim the extreme edge of the shallow reef flat. As the lower fuselage contacted the ocean surface, the hydrodynamic drag initiated rapid deceleration. However, the kinetic energy of a bomber weighing tens of thousands of pounds could not be instantly dispersed by water friction alone. The airframe experienced a hydrodynamic overshoot. Instead of grounding firmly onto the coral shelf where the aircraft would stop immediately, the forward momentum carried the bomber straight across the reef edge. The aircraft glided past the shallow plateau and settled into the open, deeper water beyond the drop-off. The wreck's present condition is consistent with Moore's low-angle ditching path, but the impact still injured several crewmen and damaged the airframe. Because the bomber did not immediately break apart, trapped air remained in the fuselage long enough for a rapid evacuation. All 10 crew members abandoned the aircraft before it slipped beneath the surface, leaving the machine intact enough to become both survival vessel and sealed historical site. As the bomber filled with water, it lost buoyancy and settled upright on sand just beyond the reef edge, at roughly 150 to 165 feet, depending on the source and measurement reference. That position spared the wreck from the harsher violence and stripping risks of the shallow reef flat, while placing it in a zone that would complicate every later survey. The exact mechanical trouble that crippled the 2 right-wing engines remained submerged, locked inside the engine cowlings of the sunken airframe. The final location of the wreckage survived through a mixture of crew memory, local knowledge, and wartime reporting from the coast. Local villagers and a coastwatcher presence near the area helped anchor the story to a real place, even after the ocean erased any floating surface markers above the wreck. With the airframe resting beyond easy salvage or casual discovery, a distinct investigative problem emerged. Investigators would eventually have to determine how a dive team could relocate the target 43 years later by following local reports and searching the reef edge in exceptionally clear water. For 43 years, the reef edge near Boga Boga held the wreck largely undisturbed. In 1986, Rod Pierce, Bruce Johnson, and David Pennefather followed those local reports to the reef edge and began a focused visual search. Their primary localization method required no side-scan sonar or heavy search equipment. Instead, the team relied on the exceptional natural water clarity off Cape Vogel. While searching along the fringing reef, Pierce visually acquired the intact tail section emerging from the shadows of the sea floor. The visual discovery confirmed the existence of the airframe, but it immediately introduced a rigid physiological boundary. At that depth, useful work time is consumed quickly by gas reserves and decompression planning. Hand measurement, sketching, or extended inspection of a single cowling would slow the broader survey and increase risk. To circumvent this strict time barrier, modern investigators adopted high-speed optical methods. In 2023, a research team from Curtin University utilized advanced processing to reconstruct the entire site digitally. They compiled thousands of high-resolution photographs captured by recreational divers moving continuously over the wreck. This rapid capture method bypasses the bottom time limit. Divers do not stop to measure or analyze. They simply swim a structured grid while taking overlapping images, allowing them to cover massive sections of the bomber within their tight physiological windows. The university researchers fed overlapping 2-dimensional photographs into specialized software to generate a photogrammetric reconstruction of the site. This computational process identifies matching features across multiple images taken from varying angles. By calculating the slight perspective shifts of these matched features, the software estimates the spatial location of visible points in a 3-dimensional grid. Image processing can improve contrast and visual interpretation in the underwater photographs, but underwater color and lighting remain difficult variables. The result is a detailed, high-resolution digital model of the visible wreck, not a claim that every hidden surface has been measured to millimeter accuracy. The non-contact model let researchers inspect the wreck from the surface and preserve the visible combination of continuity, impact damage, and long-term exposure without touching the fragile structure. The point cloud settled the external record, but identity required one clue the model could not supply: the aircraft radio call plate mounted inside the cockpit. That plate connected the wreckage to the serial number 41-24521 and tied the airframe to its operational history. Because the divers could not create a new access point through the fuselage, they had to work through existing openings in the aircraft. The open bomb bay doors offered a route into the lower fuselage, but that route carried the hazards of darkness, silt, and snagging, inside a wartime bomber resting at depth. Inside that route, darkness, suspended sediment, and wartime fittings turned navigation into the main risk. In 1986, Bruce Johnson made the required internal penetration. To reach the cockpit, he had to thread his way through the cramped bomb bay while avoiding suspended cables and disturbed sediment. A single misjudged fin kick could have caused a silt-out, instantly reducing visibility and complicating the exit path. The decision to risk the internal penetration was weighed directly against the need to identify the aircraft. The team recognized that an external survey alone could not lock down the specific historical identity of the bomber. Johnson successfully navigated the bomb bay, reached the cockpit, and used handheld lights to locate the radio call plate on the main instrument panel. The plate confirmed the aircraft as serial number 41-24521. Contemporary accounts state that it was retrieved, so the 1986 identification should be separated from the stricter, non-intrusive standards used in modern digital documentation. The final two digits, 21, also explain the crew's nickname for the bomber, Blackjack. The internal navigation confirmed the primary identity, but it also defined the next proof ceiling. Other critical evidence remained inaccessible without moving structure, clearing sediment, opening components, or lifting the failed engines for teardown. Engineers could not inspect the master rods, cylinder banks, oil lines, fuel systems, or engine control systems, so the exact cause of the dual right-wing engine trouble remained beyond direct physical verification. The ditching dynamics impose a second limit. In a breakup case, engineers can use the spread of detached engines, wing structures, and tail sections to estimate touchdown energy and sequence. At Boga Boga, that tool is largely unavailable. The wreck is largely concentrated as a single cohesive aircraft, leaving far fewer scattered impact clues on the reef shelf to measure. The concentrated wreck forces interpretation back onto the main body. It confirms the broad survival pattern of the airframe, but it cannot establish Moore's exact heading, touchdown angle, speed, or final approach precision. While the macro structure remains unbroken, interpreting the finer details of the aluminum skin is severely hindered by the ocean environment. Decades of deep water immersion have covered the bomber in thick marine growth incrustation. This biofouling camouflage obscures critical visual data, hiding panel gaps, rivet lines, and minor structural deformations. What appears to a visual sensor as a solid coral formation is actually a crucial engine exhaust stack or a flight control surface linkage. The encrustation masks the fine mechanical details that might otherwise indicate pre-impact damage, localized heat stress, or internal fire boundaries. Investigators cannot scrape away this marine growth to reveal the bare metal without violating the absolute zero disturbance mandate. The interpretive limits extend far beyond the engine cowlings to the central structural spine of the aircraft. As the heavy bomber settled onto the sandy sea floor, its massive weight displaced the loose bottom material. The aircraft sank partially into the ocean floor, bearing the lowest sections of the airframe. The internal lower fuselage and the critical central wing spar connections remain completely obscured by deep sediment. This burial blocks any visual inspection of the lower bulkheads and the primary load-bearing paths that connected the fuselage to the wings. Together, the encrustation and burial mark the responsible end of the visual survey. Investigators mapped the intact form and validated broad structural survival, but the site's hidden mechanics remain beyond a non-intrusive verdict. The preservation of Blackjack at Boga Boga creates the final management trade-off. The wreck can be protected as heritage but not physically rescued from the ocean that is slowly consuming it. When the military accepted delivery of the Boeing B-17F in 1942, the airframe cost $314,109. Today, the same aluminum structure is an irreplaceable baseline, not a recoverable asset. Management therefore shifts to non-intrusive monitoring. Each later survey compares the visible airframe against the previous optical record, allowing engineers to track fuselage sagging or wing root collapse over time through visible change alone. The 2023 Curtin University model now serves as that baseline record, preserving the wreck's visible shape, orientation, and structural condition for comparison against future surveys. With the model in place, approved researchers and disciplined dive teams can use the wreck as a baseline target for future optical updates, rather than as a source of recoverable artifacts. The National Heritage Framework supports a separation between physical investigation and structural preservation. It reduces the chance that the final resting place of the aircraft will be dismantled by salvage crews or stripped by artifact hunters. The external structural geometry is now preserved in the digital realm, but the physical material remains exposed to saltwater, marine growth, and the long-term corrosion risks faced by historic aluminum aircraft in chloride-rich environments. The non-intervention approach means that researchers must watch the structure change rather than assume they can stabilize every failing joint or frame. The physical bomber will likely continue to degrade under the ocean environment, and some parts of the airframe may eventually lose their load-bearing integrity. The non-contact survey achieved a definitive success by mapping the airframe during a rare window of major structural continuity. The Curtin University digital model now stands as a critical baseline record of the intact machine. How long will the physical aluminum framework hold its shape against the deep ocean chemistry before the digital record becomes the clearest surviving image of Blackjack?